capacity. So heat capacity, I won't write it down. Well, do you remember what it is? Don't say it's the capacity of the whole heat. I will come down there. What is heat capacity? Or the specific heat capacity. The capacity of the whole heat specifically. Specific heat capacity, yes, do you want to go first? Specific heat capacity of a material is the energy required to raise the temperature of 1 unit mass of that material by 1 unit degree of temperature. Not changing the state, of course. So I won't write that down, that's in your notes anyway, it's a standard definition. I'm more worried about the calculations. Right, so the calculations. You've got a copper can, and it has a mass of 0.18 kilograms, and there's some water inside, and this is 0.434 kilograms. The temperature is 5 Celsius, and then you have a block inside of it, and this block is of mass 0.356 kilograms, and its temperature is a cold -184 Celsius. Now, do we know the temperature of the tank? Well, I assume it's the same as the water. Yeah. He doesn't say that it's at equilibrium, but we'll assume it's at equilibrium. So both are at 5 Celsius. Now, this is put inside of it, and the result of putting this inside is that the whole system, its temperature will become 0. Yeah. Okay, so what is the thing which is gaining heat here? What is gaining heat?
The aluminium.
The block.
Yeah.
And what's losing heat? Water and the copper. And some of this water will actually become ice as well. So anyways, what we should work out first is how much energy, the energy gained by the aluminium. Is this aluminium? No, this one is aluminium here. So that is mc delta theta, which is 0.356 times 0.91 times 10 to the 3 times 184. Which is 59609. Yeah, it's heat change. 0 to minus 184 to 0. Okay, so that's how much energy the block gained, which means that's how much energy was lost by the water and the copper. So what happens is now the copper, there's some energy lost by the copper, there's some energy lost from the water. This is copper, this is water, and some ice is produced, but we don't know how much. So yeah, I'll say XL because we don't know the mass. So we have 59609, correct, equals 0.18 times 0.39 times 10 to the 3 times 5 plus 0.434 times, what is it, 4200 times 5 plus x times L, which is 334000. I'm squeezing in all my numbers, but it's just solving this. So I got 150 grams. Let us hope it is right. And it is. Result. So 0.15 kilograms is correct for X. I can go down. Liquid nitrogen of temperature minus 196. A block of copper mass, which is at temperature 220, is lowered into liquid nitrogen. Cool. So you have your liquid nitrogen, and this is at minus 196 Celsius. And then you have a block here, and this block is 0.35 kilograms, and it's 20 Celsius. We don't know the mass of the liquid nitrogen, x kilograms, and what happens is the block gets put in, and the temperature of the block falls to minus 196, and some of the nitrogen changes into a gas. So the question is, what's the mass? Okay, so what is gain in heat here? What is gain in heat? The nitrogen is gain in heat. And what is lose in heat? The block. So the nitrogen gains heat in the form of vaporizing the gas. So that's ml or xl. And the block loses energy in the form of just mc delta T. So that means the X is mc delta theta over L. So what is the mass? It's 0.35. The C for copper is in the previous question. The delta theta is, what's the temperature afterwards? Minus 196 as well. Okay, so it has a big loss.
Is minus 1,000?
Yeah, we don't put minuses in here though. And then the L is 199 kilo. So I got here 148 grams, which is right. Okay, part D.
What do you use for L?
The L is given there, 199 kilo. Yep. Part D. You have 20.45 grams of nitrogen. Goodness sake. Of nitrogen. The volume is 30.4 times 10 to the minus 3 meters cubed. The temperature is 20 Celsius, and the relative atomic mass is 14. And it's a diatomic molecule. Diatomic meaning it's N2. No, I don't like that you use the word diatomic, because that's a chemistry word. I don't think it's something we really say in physics. We haven't really said in class, diatomic. But you know it's from chemistry, so diatomic meaning it's N2. Which that sucks, but whatever. And the mass is 14, so that means 1 mole will be equivalent to 14 grams. So we have over a mole here. Right, so what's the pressure? So you have PV equals N or T. Actually, let's work out how many moles we have before we do anything. We have 1.46 moles. Okay, so that means P is N or T over V. The N, I have it on the calculator. The R is 8.31. The T is 273 plus 20. And the V is 30.4 times 10 to the power of minus 3. So I get a pressure in the kilos, maybe.
How do you get N is 1.46?
Oh, you know how I did it, KJ. You tell me.
1.45 and 14, just take the ratio.
20.45 divided by 14, isn't it?
Yeah.
But I'm wrong.
This is 20 points. What?
Is the mass not 20.45?
Yes.
Ah, rats. I forgot. Diatomic.
But
So, wait, hang on. Nitrogen has a mass of 14 and it's diatomic.
it's like 2.
So one more is 30,
So,
20.
the relative mass is the mass for 1 mole of the molecule or of the atom?
Out of the molecule.
I think he's right. I think it's the atom. So that would mean then that the molecular mass is twice this.
Yeah.
So that means my N is it's too small. It's twice as big as this. Is that it?
No.
No? Or it's too big?
No, 1 mole is 28 grams because it's the diatomic molecule. The relative atomic mass is the atomic mass of one atom.
Okay, so my N is too big.
Yes.
So I should divide it by 2.
Yes.
Fine. So I need to divide this by 2, which means I need to divide this by 2. Chemistry. So I should have 58 okay, so that's right. 58.5 kilopascals. Too chemistry for me. I don't like it. Right, part 2 is the volume changes. No. What happens? Oh no, it's just changed the temperature. Wait, the next part is just change the temperature. So do this exact same thing, except use a different temperature. Silly. Right, so do you see here, the only thing that changes is the T. So if you just put in the T as 273 instead, you'll get 1 point, well, sorry, they're looking for the, what are they looking for? The volume. So you have V equals N or T over P. So they change the temperature and the pressure, but no big deal. Just put in the different numbers. Put in the different numbers, you get 1.64 times 10 to the minus 2 meters cubed.
If you put temperature 0, oh, no difference.
You don't put the temperature 0 because you use Kelvin.
Yeah.
Right.
Do some.
The next part is how many nitrogen molecules are in this gas sample. Well, sorry, can you just tell me what was the N previously? It was 1.46 divided by 2. Okay. Actually, I need to check something here. Times 8.31 times 273.15 divided by 1.01. Yeah, that's correct. Okay. Part 3 is how many... No, it can't be that simple. How many molecules of that nitrogen do you have? Well, well, the N, what did I say the N was? 0.73. That's moles of N2.
Yeah.
So the number of nitrogen atoms would be 2 times 0.73 times Avogadro. And Avogadro is number 24 on the calculator. So I got not correct. No, I'm misreading. He didn't say how many atoms. What did he say? How many molecules? Molecules. So we don't want the 2 here. He wants the molecules, not the nitrogen atoms.
Just 0.73.
Yeah. That is correct. 4.396 times 10 to the 23 N2 molecules. Right, and the last part is what is the density of nitrogen? So the density is the mass over the volume. Now we know what the mass is. It is 0.02045, and we know what the volume is. It is 30.4 times 10 to the minus 3, and we know how to divide. So my volume is a small 0.673 kilograms per meter cubed, which ain't right. But why? My bad. He doesn't want the density from the beginning of the question. He wants the density later when it's at a colder temperature of 0. So what? The mass is still the same, but what is the volume we worked out recently? What was it? Wait, before you calculate it, if it gets colder, what will happen to the density of the nitrogen gas? Will it go up or go down? It will increase. Yeah. Yeah. 6.9 or 6.4?
4.
Need to work on my 4s. Yeah, it is 1.25 kilograms per meter cubed, which is correct.
You're gonna practice that in 4?
I'd have to do. Yeah, I have to, seriously. All right, we'll finish up with fields. Nice. So then we'll have a look. How many more physics classes do we have? 3?
Yeah.
Great. So we'll get the example I've done in those 3. Hopefully. If not, we can use some of the math time.